In this lesson, we're going to learn the method of point estimation. There will be two methods that we're going to learn. One is the method of moments. The other one is method of maximum likelihood. Both methods will try to help us to derive the estimate when we know the distribution of the data. In the two methods, the maximum likelihood estimate tend to give a better estimator in the sense that this estimator will have certain properties attached to that. These properties are very desirable in the sense that it will guarantee that the estimator will be approximately minimum variance and biased estimate, and also has an invariance principle that's going to be easy to get MLE of functions of the simple parameters. But unfortunately, the MLE involves quite a lot more computation than the moment estimate. We'll first learn the moment estimate. The moment estimate, also referred as method of moments, simply using the population moments to estimate using the sample moments to estimate the population moments. The unknown parameters mostly are actually related to population moments. For example, when we have the data from normal, we would have unknown parameter mu and unknown parameter sigma. The mu and sigma are related to the first two moments of the population. So first, what is the moment? When we have a distribution with PDF given by f of x, then the population moment refers to an expected value of x to the power of k. And the sample moment is given by x to the power of k computed from the sample and then take the average. So we use the sample moment, this quantity, to estimate the population moment. Example, the x bar is the first moment calculated from the sample, and the mu is the first moment computed from the population. Basically, we relate the population moment with the sample moment, but the population moment itself may not be a single parameter. It might involve multiple parameters or be functions of multiple parameters. If the probability mass function or probability distribution function involves multiple parameters, theta 1, theta 2, up to theta m, in that case, we'll use the m of the moments. First moment from the sample, second moment from the sample, up to mth moment from the sample to make them estimate the population moments, and then that will give us m equations. From the m equations, we'll try to solve for the m unknown parameters. So that's his method of the moment. For example, when we have the mu and variance, the expected value and expected value of x squared, these are the first and second moment. And this moment, we can refer them as theta 1, theta 2. And then when we consider the expected value of the data, this expected value would be mean, and the expected value of x squared, on the other hand, will be equal to, let's see, expected value of x squared is equal to expected value of the x minus the mu plus mu, and then you square it. And the minus mu plus mu will cancel out. And afterward, we put the x minus mu together, squared, and the mu squared, and then the twice of the mu and the x minus mu take the expected value. So this twice of x minus mu taking expected value is 0 because x is centered at mu. Therefore, this term will be gone. That's just 0. And what's left is the variance sigma squared plus the mu squared. So this side is the left-hand side is the expected of x squared. Then we will use we'll use sample moment, second moment. So we use I equals from 1 to n and then xi squared to estimate this one. So make it equal to sigma squared plus mu squared. And then we will also need here I'm using hat already, because when I put in the sample, I'm not really having the sample equal to the population quantity. It's an estimate of is sigma squared and estimate of the mu squared together give us the average of xi squared. And we also had this first moment, which is the sum of the xi's that give us the estimate of the mu. So these two will give us two equations, and we solve for the mu hat and the sigma hat. So if we do solve for that, we'll find that the mu hat in this case is the average because of the second equation. And the first one, the sigma hat square, would be simply estimated by 1 over n summation of xi squared minus the x bar squared. This, if we simplify it, it's going to be equal to this one, xi minus the x bar squared. This is because when you try to extend the squared term again, the cross term and the x bar squared term will become like one will become like the twice of the other. Okay, this gives us the moment estimate of the sigma squared. Let's see, here's an example for a random sample of service times of n customers at a facility. The underlying distribution is assumed to have exponential distribution with parameter lambda. For this distribution, the probability density function is given by lambda e to the negative lambda x for x greater than 0. And if x is not greater than 0, the PDF is 0. So for this case, when we calculate the expected value, E of x will be 1 over lambda. And so simply integrate x with the density, you'll get this one, okay? So we make the moment estimate, we get the moment estimate by equating this first moment equal to the sample moment. So summation of the observed xi, make it equal to the expected value of xi, so which is 1 over lambda. But since we are doing the estimate, this is 1 over lambda hat is equal to that. This will give us our lambda hat moment estimate to be 1 over the x bar average. Because left-hand side is simply the x bar. Okay, this is that x bar, and right-hand side is 1 over lambda hat. So lambda hat becomes 1 over x bar. This one was the moment estimate. And if we have data collected, we simply use 1 over x bar. That gives us a moment estimate value. Okay, so that's about the moment estimate. I will record a separate video for the maximum likelihood estimate.